Okay, I'd like to begin this lecture series by just talking about functions. And the reason is calculus is performed on functions. You have to have functions if you're going to have calculus. And unfortunately, I believe most people have more of a, rudimentary understanding of functions. F of x equals x squared is not necessarily good enough. So let's talk about what functions are and review this. Okay? So in order to get there, we need to define the Cartesian product of two sets x and y. Okay, the Cartesian product of two sets is the set of all ordered pairs, or we write it x and y, where x is a function of x, y is a function element of y. Now again, ordered pairs isn't a random term here. I'm trying not in this class to just introduce terminology for the fun of it. Ordered pairs mean two, and order matters, right? The x is the first, x comes from this set, and the y comes second. Now you can say, well, okay, what does an unordered pair have to do with anything? Well, it does. In probability theorem, you have unordered pairs. So 2, 1 is the same as 1, 2. So this does matter, okay? So we're talking about ordered pairs. The first one is going to come from, in fact, for us, the domain, and the second one is going to be an element of the range. And again, what I'm going to do is introduce the function when the sets have a finite number of elements in them. The challenge for us is how to extend this to, say, when x is the set of real numbers and y is a set of real numbers. Right? The difference is when you have a finite number of elements in each set, you can just literally list them out. How are you going to list them out if you have infinitely many, or if the set is the set of differentiable functions on an interval? Okay, so keep that in mind as we go forward. Okay, so this is my set x, 1, 2, 3, 4, 5. The set y is a, b, c. The key here is that they're ordered, right? 2 is more than 1, 3 is more than 2, b is more than a, c is more than b. So the Cartesian product would be, okay, the Cartesian product would be an ordered pair, set of ordered pairs. So I take 1a, 1b, 1c, right? And then I shift to the next. 2a, 2b, 2c, and so forth, 3a, 3b, okay, we get the jokes, right? So as long as the set is only finite, you can, in principle, write everything out. Now the Cartesian product is the backdrop on which the function is painted, okay? A function f written from x to y, so x will be the domain and the range will be contained in y, and just depending on notation, you can represent this such a way or such a way. And you can say, well, f of x equals x squared. Look, that's just too simple. So we need something a little more sophisticated to do calculus. Okay, so a function is a subset of this Cartesian product, such that every element of x is the first component and one and only one ordered pair of the subset. Okay, so let's look at this. Here's a function from x. That's going to be my domain, to y. My range is going to be contained in this set. Okay, here it is. I'm just rewriting this. This is my Cartesian product. So we need a subset of this such that we hit all the x values, and only for every x value, only one y value. That is a function. The function is literally this set. Literally, it's this set. Again, think about how you're going to do this if x is, for example, the set of all real numbers and y is a set of all real numbers, right? The problem is how we are going to list them all out. We're going to need shortcut methods. What if x is a set of all differentiable functions on the interval 0 to 1, right? I mean, how would you handle that? All right, these are the real issues we're dealing with here. Now, in terms of a notation, we write generically y equals a function of x to denote this relationship, right? Y equals a function of, the brackets are shorthand for of, x. So if we want to represent this set in this notation, we can write f of 1 equals c, f of 2 equals c, f of 3 equals b, and so on. These are all equivalent ways of writing the set. Now again, keep this in mind. What might the advantage to this be? All right, what might the advantage to this be? it can play out, for example, when x is the real number. So keep this in mind, right? What's the advantage here? How can we generalize this? Okay? So the domain of f, in fact, is x is the domain of f, and the range of f is just contained in the set y. So usually with the range, we're just saying it's a real number versus it's a complex number or a square matrix or something like that. And the range will be contained in that set. It's very hard to determine a range in general. Let's look at this graphically. Right? So I have the Cartesian plane. Notice that the x values are along this axis, the horizontal, and the y values are represented along the vertical axis. So in particular, x is literally this set, these dots, 1, 2, 3, 4, 5, and y is literally these dots, A, B, C, right? So little x takes one of these values. Little x is only a placeholder. It can equal 1, 2, 3, 4, or 5. You have to tell me y is one of these values, A, B, or C. So our Cartesian product in this picture are these dots. And our function is literally a subset, are these dots. So the function is literally these dots. Okay, so this, if you do it graphically, this is called the graph of the function. Right? This is the graph of the function. Again, you can see the graphs of functions that, well, have infinite number of points, and that's the connection. So there's different ways we can represent a function. We can literally write it out. We can draw a picture, okay? And this is how we're going to try to generalize to the set of all real numbers, for example, for the domain and range. And again, that's the problem when the sets are not finite. Finite is always easy. Maybe a large set, but you can literally list everything out. Okay, now let's look at the one, maybe an example you're most familiar with, f of x equals x squared. That's a very fine function. Is it a function? Well, not technically in the way it's given here. This is only the rule associated with the function. Now, the idea here is we need a domain and range, right? So here's the definition. And again, just Google this. You don't have to believe me. This is just a definition. A function f from x to y written in such a way is a subset of the Cartesian product xy. So at the minimum, I have to tell you the sets xy. Now notice, in this simple case, it's understood that you can figure this out yourself. Right? It's a shortcut. So I'm saying I'm too lazy to write it out. You figure it out, and you can. You could actually also choose complex numbers here. You can square complex numbers and so forth. So you can also have chosen complex numbers, for example, square matrices. But the assumption is that you're going to choose the real numbers. It's real variable calculus. Okay, but it is an assumption. I give you the rule. You have to figure this all out. Okay, so pros and cons. Again, it's not about right or wrong or better or right. Pros and cons are advantages and disadvantages. The advantage of just listing this is it's short. The disadvantage is this is your problem now. In terms of the picture, notice my set x now is the entire horizontal axis, and my set y is the entire vertical axis. Again, x is just represents any of these numbers. So x can be 1, 2, 3 halves, pi. X can be any number here. Now, this is the idea. I have to have, for a function, I need xy pairs. I didn't give you that, but this notation is the connection. For every x, you can compute a value of y. And this is one way we get around the fact that we have to list everything, every ordered pair. So I'm telling you what the domain is, and the range is contained in this set, and I'm saying for any element in x, you can go to this formula and compute a value of y. And I can represent all those ordered pairs on this graph, the graph of the function f. So this is one of the ways we bypass the fact that the set is not finite. The set x and y are not finite. We can't list them all out. Well, we can, but we can tell you how to compute them is the idea. And again, to do calculus, you need functions. Okay? So our subset of the Cartesian product is this. Now let's see how we can play this game. Now notice I'm taking g, I didn't call it f, g. The rule is the same, x squared. But notice I'm telling you explicitly that the domain is only the non-negative numbers. Is this the same function? Well, let's look at the picture. The graph of g would only contain these xy pairs. Notice x is only the positive part of the horizontal axis, or the non-negative part of the horizontal axis, right? It only starts at 0 and it goes out. So clearly this represents a different set, right? These are different elements. So with respect to the functions f and g, we have different things, right? This guy's happy. Their domains are different. The domain of the function f was the real numbers. The domain of g is only the non-negative. So again, a function is three things. I need a rule, I need a set, a domain set x, and I need a set y which contains the range. So these functions have different domains. Notice the range is contained in the real numbers in both cases, and the relationship, or their rule, is the same. But it's not enough that 2 out of 3 are okay. We have to meet all the conditions. Since all the three conditions, okay, the set x, the domain, the set y, and the rule have to be the same for them to be the same function, these functions are not equivalent. They're not the same. I'm going to use the notation, okay, not an equal sign, 3 bars in the line. It's an equal sign equates two things. The 3 bars, okay, I'm a math guy, you don't have to do it, but equates everything. So a function contains the rule, the set y and the set x. Okay, so that's the distinction. These are not the same function. And you can see that, right, if we look at the graph. They're not the same. Now, what I'm going to take the approach in this course is I always want to do things the same way. I'm not trying to make easy problems hard. I'm trying to do everything the same way so you get comfortable with that. So the function itself is labeled f. This isn't unique to me. The function f is only f. That means all three of these things. The rule is here, right? F of x equals x squared. The set x is the domain, is the real numbers, and the range is contained in the set y. And the set g, again, just g means all three of these things. The rule is x squared. The domain is the set x, is the non-negative numbers. And again, the range is contained in the set y, it's all the real numbers. And you can see that they don't represent the same ordered pairs. Now you could say, could I take y to be the set of 0 to infinity? Yes, you could. I mean, you could, but it doesn't change anything at all. So I don't have to work too hard for y, right? The range is just contained. When I'm saying y is the real numbers, I'm saying it's not the complex numbers. It's not square matrices. It's not the set of differentiable functions on an interval. So it's pretty broad because it's generally pretty hard to pin down the range. Okay, but again, physically we can see, just look at the pictures, they represent a different set of ordered pairs. Now, this is something we're going to do quite frequently. Okay, so here's another function, and let's look at this. Again, I just gave you the rule. I haven't specified the function yet. So when I write this rule, what I'm really saying is the following, right? I'm really saying, okay, you gave me the rule, but the function consists of more than that. Again, go back to the definition. The domain is the set x, so I'm not equal to 1, and the range is the set y. Okay, so a function consists of these things. Now, how do I know the range? I mean, how do I know this for the domain? Again, what I want you to get used to is you have a certain number of tools in your toolbox. What I've included on the web campus under files is what I call a crib sheet. I've listed all the algebra rules. What are there, 20 or 24, something like that I use throughout the entire course. And everything has to follow a rule. These rules are your tools. They're the tools in your toolbox. Now, we're going to concentrate primarily on calculus rules this semester, but all the same, you should be comfortable with this. K through 12, just learn these rules. And the rule we're applying here, and again, you don't have to write this down by any means, but what you should do is you should always think this. A fraction, a over b equals 0, if and only if the top is 0, right? The numerator, a equals 0. And a over b is undefined if the bottom is 0, right? And clearly what we have in this particular case is we're looking for where this expression would be undefined. So a over b is undefined if b equals 0. Here I take a to be the numerator, b is the denominator. So if I want to find out where b is 0, I have x equals 1, and this is not admissible. X equals 1 is a value for x such that this fraction is undefined, and that's where this comes from. Again, I'm not trying to belabor the point. What I'm trying to say is there are reasons for everything in this course that we're going to do. And that reason is not because somebody told me to do it this way, or I stand on my left foot, face to east, and pray to my God. These are not math reasons. Math is given by, well, rules. Okay, and we'll talk about the difference between being creative in math and just doing the mechanical process. Okay, I could also define the function by its graph. So notice if I graph this, plot all the xy pairs such that y equals f of x for all these x in the domain, this is the picture I'd get. Notice the function is not defined when x equals 1. Right? It's not defined when x equals 1. But both these formulations would be equivalent. Now let's see what else we can do. Notice I've specified the rule like this. But notice as long as x is not equal to 1, I can do some simplification. I can do some canceling. For example, if I factored the top, I can factor out the x minus 1 from the top and the bottom. And x minus 1 over x minus 1 is 1. This is how things really cancel. I mean, when you're saying something cancels, it really equals 1. And 1 times anything is whatever it is. Okay? So now these two algebraic expressions are exactly the same provided x is not equal to 1, which is coincidentally, not coincidentally, what the domain is. So as long as I specify the domain, why take the complicated rule? Why not just use the simple rule? Right? And this is going to be an idea that plays out a lot in what we do. So notice if I graph this function g, I get g of x equals x plus 3, so that's the rule. And I specified a domain of g such that x is not equal to 1. Look at the graph. It's exactly the same as for f. They're exactly the same. So I'm just going to include them here. Look, they're exactly the same set of ordered pairs, right? A function is a set of ordered pairs in the Cartesian product of x and y, the domain and the range, the x and y sets. Okay? So they're exactly the same. So again, let's look at pro and con. It's not one is right or wrong. These are equivalent. They are the same thing. So what is the advantage and disadvantage of each of them? Let me go back here. What is the advantage? Well, on the left where we specify f, notice the advantage was I only gave you the rule. You had to come up with the set x and the set y. That was your problem. So the pro, maybe it's easier just to specify this. What's the con? Well, these are the same. The con is, well, look at g of x. It's much easier. It's a much easier rule. It's a much easier rule. What's the con? What's the negative involved with this? Well, I have to tell you the domain setting explicitly. So, okay, pros and cons. Maybe I only have to write the one line, but the one line is more complicated, and then you have to figure out the set x and y here. If I do this function, g, the rule is easier, but I have to specify the domain and range. I guess I have a typo here. It should be range of g. All right, so again, it's not right or wrong. It depends on what you're trying to do. If I'm trying to do take the derivative, for example, I'd rather take the derivative of this than this. So again, it just depends on what you're doing with the problem. If I'm trying to define where the function is undefined, well, this form obviously helps me make that deduction. Okay, so they're the same function. They each have advantages and disadvantages, but you can see from all the xy pairs, they're exactly the same. How about a function that's given piecewise? That's what's going on here. This is a simple piecewise function. It's given in pieces. Notice there's not two functions here. It's given in two pieces. How do we interpret that? Well, let's read what this says. So the rule associated with f is, I'm saying this is how you interpret this. If x is a number, right, x has to be a number, and if that number is less than 0, then the rule is f of x equals minus x. If x is a number greater than or equal to 0, then the rule is f of x equals x. Okay, so that's how you can interpret it. You don't need to use this notation. This notation itself would be acceptable. Okay, so let's look at the top. But this is the way it's done. So let's look at the top case. If x is a number less than 0, then f of x equals minus x. So let's look at an example. What happens with minus 2? Right? Certainly what we want to do is, x is really a placeholder. It's a memory location, right? We have to put something in that address. It's just a placeholder. We could also write it as a box. This is just a notation that was developed in the early 1900s or late 1800s. We could just develop it today and say it's a box. Whatever goes in this box gets placed over here. X is just nothing more than a placeholder. In this particular case, I'm going to say x, what goes in the box, is minus 2. So if minus 2 goes in the box here, I have to put it in the box over here. Minus 2 is 2. Okay, that's how we use it. In the case that x is a number greater than or equal to 0, then f of x equals just x. And again, how would that work? Let's look at always special cases. How about f of 2? So again, I'm just going to simply replace x, cut and paste, x is just a box, with a 2. So I'm going to put it on here, and I put it in the box over here, so f of 2 is 2. And you'll see we're going to be having this play out all throughout what we're doing in more complicated situations. Now, they didn't tell us the domain or range, but this rule works, we can figure it out ourselves, for all real numbers. And the range, of course, is going to be everything with real numbers. In fact, the set y of the real numbers. In fact, the range is going to be non-negative, as we'll see. But at any rate, specifying the y set is the set of real numbers is fine. We're saying it's not the set of complex numbers or square matrices. But we did have to determine this. That's part of defining the function. This is only the rule. And here's the picture. It's going to be the absolute value. But notice the set x is the real axis, is the horizontal axis, and the set y is the vertical axis. Again, when I say little x, I have to plug a value in. It's going to be 1, 2, pi. If I pick y, it's going to be one of these numbers here. And again, all the xy pairs on this red line belong in a set, and that set is, by definition, the function. Okay? Now let's talk about where this comes from. I could just call it f, but it's a relatively common function, so you can't just keep calling everything f. So the notation we used was originally 2 bars, right? Just 2 bars. But that's kind of sloppy, right? It's just 2 lines, 2 lines, 2 lines, right? But okay, now I'm getting lazy. That's a lot of work for someone like me. So, okay, I'm just going to be redundant here. It's not the best. It's a corruption of the notation. But I'm just going to put the 2 in between the 2 bars, the minus 2 between the 2 bars, and be done with it. So when I write an absolute value notation like this, I'm really saying using a function notation where the function is 2 bars, right? The absolute value function. And it's just, again, you see we do these shortcuts always, and you lose track of what they mean or what it stands for. So 2 bars just means the function is the 2-bar function, the absolute value function. Okay, so I'm really saying f of x, again, this font isn't right, but is this piecewise function. Again, it's not 2 functions, right? It has 2 different rules depending on the x value I choose, but it's 1 function. And in fact, you could represent it like this if you like, right? The function is the 2 bars. Here's the rule, right? This tells me how to actually compute it. The domain, which is the set x, is the set of real numbers. And the range is contained in the set of real numbers. In fact, the range is just the non-negative numbers, but it doesn't matter. It's still a subset of the real numbers. Okay, so given that I have this function, right? And again, when I write this rule, you should understand, I mean, you don't have to write it, but it means that, well, the domain of this function is a set of real numbers, and the range is contained in the set of real numbers, right? I need the sets x and y for the definition. Again, by definition, a function needs a rule, it needs a set x and a set y. Okay, so let's continue. How would I evaluate then this quantity? Right? Now go back, we talked about this already. X is a placeholder, it's a box, right? It's a memory location. I'm going to put something in that location, y minus 3. So all we're going to do is replace all the x with y minus 3. You can see this is what it pairs up. These are the same thing. So everywhere I have an x, I'm just going to cut and paste a y over y minus 3. That's it. Now, what I want to do is I want to clean this up. I want to know what values here. I don't want to have to solve another equation. This isn't very hard, but sometimes it can be, as you'll see. So instead of writing y minus 3 less than 0, I'm just going to clean it up and write, well, y less than 3 is this rule. I distributed the minus sign. And y greater than 3, because what I'm saying is now this function is, if y is less than 3, use this rule. If y is greater than or equal to 3, use this rule. And that's its own function. It's a function of y if I choose to call it something else. In fact, it's composition of functions, but whatever. Okay, we'll come back to that idea later. Let's look at some other special cases here. And I guess what we're trying to do is work on this idea of what a function is. So I'm going to say let a function f, and I'm going to say it's defined such that its domain, its set x, is only the non-negative numbers. And I'm going to say it has to satisfy the rule, relationship, that its y values, right, the y set, y equals f of x, the y set are non-negative. And the connection between x and y is given by this equation, x squared equals y. Notice this is an equation. This is not a function. Okay? So I'm specifying this function implicitly by specifying the domain, the range, and this algebraic equation that relates the x and y pairs. Remember what a set is. You have to tell me the set x, the set y, and the Cartesian, the numbers, x, y pairs that make up the function. So this should presumably be enough. Let's test this case. Can I evaluate f of 4? Okay. Well, I know the set x, right? I need a function. I know I need the x, y pairs that make up the function. My set x is the non-negative numbers. This tells me that my set y is also the non-negative numbers, right? Remember, this is always underlying what's happening, right? And this example will show that. I mean, we take these things for granted, but this is part of it. So when I write f of 4, I'm saying that I want to look at the value. X takes the particular value of 4. And notice that is in my set x. If it wasn't, it's undefined. Okay, now how do I proceed? A function is an xy pair, right? Y equals f of x. I literally need a y value to pair with my number 4. Okay, so what do I know here? Again, I need a y value, and that's going to be the f of 4, right? And that has to be contained in this set, the range set. I know all this. Okay, but how do I determine that y value that goes with 4? Look at the page. What's on this page that allows you, if I tell you x is 4, to calculate the y value? That equation, right? The given equation, right? I know x squared equals y. So if you tell me x is 4, I have to calculate the particular y value. Now, how do I solve this? No. How do I solve this? Let's go here. Y squared equals 4 is the same as y squared minus 4, right? This is a polynomial. In fact, it's a quadratic. We can factor it and determine its zeros. If you want to use quadratic formula, fine. But this is pretty simple. We know there are two zeros associated with this quadratic equation. I can factor it this way, right? And then again, what is the math rule I'm going to use here? A times b equals 0, if and only if A is 0 and or B is 0. So here I have A and I have B, right? So I have to have, right, A is the y plus 2, B is y minus 2. Again, you don't have to write this, but this is what you're doing. So I have to have A is 0 and or B is 0. And I can solve it and says y equals minus 2 or y equals 2. Okay, let's go back. I solved this equation. This is not a function. I solved this equation for y values, right? I solved this equation for y values. Okay, so that's great, but that's not what I'm looking for. I need to determine what f of 4 is, right? I'm not interested in solving an equation. I have a function. A function is defined implicitly by this equation. So I have y equals minus 2 and or y equals 2. What's the problem? Well, the problem is the range of the function has to be non-negative numbers. So I cannot include this value. I mean, I can't. By definition, I'm telling you that I will only accept y values that are non-negative. And so now I know that y has to be 2. Going back here, I know that f of 4 is 2. I mean, it's a roundabout way. It's an implicitly defined function. Okay, but I could determine a y value associated with f of 4. Now, let's explore this a little more because, again, this is the kind of cheap mistakes that, again, I understand where they come from, but they shouldn't happen. Notice this equation is a quadratic equation, and the quadratic equation does have two zeros, or it has two roots. They're called the square roots of 4, right? They satisfy this equation. You can plug in y equals minus 2 and y equals 2, and that's fine. It has two roots, or two zeros. That's perfectly fine. The problem is that's not what we're doing. We have a function. This is different than saying the function we define is f of 4 equals 2, right? I have to meet the criteria of the set x and the criteria of the set y being the range. So that eliminates this two values, so I can only have f of 4 equals 2. Remember, for a function, for every x value, there can only be one y value. Now this function comes up so much that it's given, again, like 2 bars, the absolute value, a special name. My theory is this f, write out f a lot, write a giant cursive f a lot of times, and it kind of turns into scribble that looks kind of like this sign. I think this is an f, a cursive, again, one of these fancy cursive f's that got a little sloppy. And again, this is too hard for us. I don't want to write this and that, so I simplify it to write it like this, just as I did with the 2 bars. I mean, again, this stuff isn't ordered. This didn't come down from the mountain with Moses. People did this kind of stuff, and they did it for their convenience. So this is the square root function, and it's a function. Notice when I write this symbol here, I, by definition, again, Google it, look in your book. By definition, I'm talking about a function. I'm talking about a function, and a function can only have one value, right? A function can't possibly equal plus or minus 2, right? And this is the problem. You can never have square root, I don't know why it's got jumped down. Square root of 4 cannot equal plus or minus 2. If you're talking to someone, you're talking to a tutor, and they tell you square root of 4 using the square root function is plus or minus 2, walk away. They don't know what they're talking about. And they're going to tutor you. In other words, when you use this symbol, you are designating the square root function. Ask them that. How can a function have two values plus or minus 2? It can. I mean, this is why there's uncertainty in when you do calculus. It's somebody tells me this sometimes, other times. That's not how it works. Square root of 4 function is not sometimes 2, sometimes plus or minus 2, sometimes minus 2. That's not how it works. It's not a mystic experience. Again, everything is precise. I don't want you sitting there, I'm not asking your opinion, I don't want you sitting there saying, I'm going to stand on my left foot, face to east, and chant to my God and pray for an answer. That's not math. I mean, it's a mystic experience possibly, but it's not math. Everything we're going to do is precise. We're not going to be making it up. So again, just look it up. This is the square root function, the symbol for the square root function. Functions are single valued. This is 2. And this value is defined by that equation. In other words, how do you know the square root of 9 is 3? The square root function of 9 is 3, because 3 squared is 9. How do you know the square root function of 4 is 2? Because 2 squared is 4. They satisfy the defining algebraic equation. This function is defined implicitly. Here's another function that's going to come up a lot. Now, I'm not going to beat you down with this on a test, so I want you to understand what we're doing. So it's not, again, some random thing or somebody told you something. So here's another one. Let this function f be defined implicitly by this equation. And as an example, let's determine f of 8. Just as an example. Okay? So how do we proceed? We have to figure out the sets x and y. Now you'll notice, if I take y to be anything I want, x can never be 0 or negative. Try anything you want. If y is 2, 2 squared is 4, right? That's positive. If y is minus 2, this is 2 to the minus 2, which is 1/4, which is still positive. Take anything you want and you'll see that x can never be 0 or negative. So this is my set x and y, and this is the relationship that's going to define the xy pairs that constitute the function. So pick any x in here, we'll solve for a y, and that'll be the value of the function. 8 is just an example. So let's try it. Okay, so the x's always have to be positive. So let's try it. This is saying when you write f of 8, you're saying x is 8. It has to check out that it's in your set x, or it's literally not defined, right? So this says x equals 8. This symbol is an element of this set. This set is the set of all non-negative numbers. So this says 8 is a non-negative number. And again, y equals f of x. That's our notation. That's the way we use this notation, f of something. So we're searching for a y value in the set y, right? And that'll be the value of f of 8. It's going to be an xy pair. X is 8. Tell me what y is. So you're telling me with x, I need to determine y. How can I figure that out? Again, it's right in front of you. Look on the page. Can you see a relationship between x and y? Yeah, here, right? This is an equation that implicitly defines a function. You can see where this is going. We're going to eventually do implicit differentiation, right, and other things. So I have 2y equals 8, right? That's the relationship. I was told x equals 8. I plugged that in, and now I need to solve this for y. So let's just review this. Again, I'm just going to break this down and review it just as practice. How do you solve exponential equations? You have to have the same base. Now, this is an easy case, right? This is the base, this is the unknown. So the base is 2. I have to write 8 as 2 to some power. And of course, this can be tricky in general. This is an easy case. And, again, it can be tricky and you have to look at numerical ways to do this. But, okay, so then if you have the same base, it says y equals 3. And that's how we solve it. Again, it's just a review. This isn't calculus. So going back, I have y equals 3. And that's it. So I'm saying f of 8 equals y, and that y value happens to be 3. And that's how I define it, this function. So once again, I'll have a function. And I can't keep calling every function f. So whatever. Somebody came up with the idea log base 2. And that's what this function is actually called, logarithm base 2. It's a function. Notice I keep the brackets. Log is just replace f with the log base 2 sign. And I don't remember where this comes from. You could Google it at seashells. I don't know. You always see pictures in algebra books, pre-calc books about this. But it is a function. And instead of just calling it generic f, I call it log base 2. Okay, and that'll conclude what we're talking about with functions.